we have divided power cycles in two different groups. Okay, one is air standard cycles. Okay, under that we used to read the Brayton cycle, internal combustion engines like Otto cycle, dual cycle and diesel cycle, all of that. Now another part of that was Rankine cycle. Okay, that means before Rankine cycle was an example. Before that the heading was steam power plant. Okay, steam power plant. Steam power plant means what? Whatever the mixture that is been running inside the machine parts to produce work, okay, or to convert the heat into work, okay, that complete medium is steam. Okay, steam, and that steam is going to change its phase from liquid to vapor or vapor to liquid. It is going to change its phase. Okay, now in terms of the air standard cycle, what used to be there in air standard, if you take any other cycles, Brayton cycle or diesel cycle or dual cycle, we used to take air fuel mixture in some cases, or in some cases we used to take only air. Okay, for example, in Brayton cycle, in closed open Brayton cycle we used to take air fuel mixture. In closed Brayton cycle we used to take only air. Okay, in Otto cycle, diesel cycle and dual cycle we used to take air fuel mixture. Okay, in none of the places they have converted their phase, okay, or transformed into another phase of the substance which is traveling through the machine parts. Okay, like turbine, compressor, whatever the fluid has been traveling, they did not change their phase in terms of air standard cycle. Okay, but in steam power plant, what is going to be there? It is going to change its phase since the steam is there. Okay, now if you condense it at a certain pressure, it is going to become water. Okay, it is going to become water. After, if you give some heat, okay, and rise its pressure to certain level and it rises temperature, it is going to evaporate. And evaporate means what? It is going to convert into steam, but it is going to remain inside the cycle. Okay, because because the substance is not going to come out of the system. Okay, the substance is not going to come out of the system anywhere. Okay, so whatever the steam, after evaporating, the water is going to be converted to steam, but that steam will not come out of the system. That steam will again pass through the turbine or whatever the machine parts it is supposed to be transferred through. After transferring, it is going to change into water again. After that, at some places with heat addition or pressure rise, it is going to evaporate again. Okay, the substance is not going to come out of the system, and there is going to be phase change. That means the main difference is there. The working fluid inside the air standard cycle did not use to change its phase, but in steam power plant, it is going to, the substance or the working fluid is going to change its phase now. Okay, now let us start how does a steam power plant work. Now to start the working principle of a steam power plant, what is going to be there? The first step is what? The first step is, this is a pump. Okay, now this is the complete cycle which is going to work as steam power plant. So the P represents the pump. Okay, P represents pump, B represents boiler, T represents turbine, and this is nothing but a condenser. Okay, or you can say heat exchanger. Okay, this is a condenser. Now the pump, what does it do? It collects the working fluid, okay, and gives it to the boiler. Okay, it collects the working fluid and gives it to the boiler. In boiler, what happens? In boiler we give heat addition. Okay, in boiler we give heat addition, and after this heat addition, whatever the water substance that has been transferred to the boiler, okay, that means working fluid, since we are saying that it is steam power plant, only H2O is going to be there, but in different phases, in different parts of the system, the H2O is going to have different phases. Now water has been pumped out. Okay, water has been pumped out and the water has been given to the boiler. Okay, in boiler what happens? In boiler the water substance is going to get converted into steam. Okay, the water that has been transferred to the boiler, after the heat addition, it boils. Okay, boils means what? It is changing its phase from liquid to gases. Okay, that means at point 3, whatever the things you are going to receive will come out from boiler, and that would be in complete gaseous state. Okay, now this would be in complete gaseous state. Now while passing this, it will come into turbine. Okay, it will come into turbine. In that means after the amount of water is getting boiled. Okay, after the amount of water is getting boiled in the boiler, the temperature of that gaseous substance is going to get higher. Temperature is going to get higher, pressure is also going to get higher. Okay, so high pressure and high temperature steam is now going to pass through the turbine. Okay, and while the high temperature and high pressure turbine is going to pass through the turbine, it is going to produce some work. Okay, so at the exit of the turbine, okay, at the exit of the turbine, after expanding, okay, after expanding the high pressure gas and high pressure high temperature gas that has been coming out from the boiler, after expanding it, some of the vapor or some of the steam is going to get converted into liquid, but temperature would be same. Okay, because whatever the things that will come out of the turbine is going to be either complete liquid or saturated vapor. Saturated vapor is what we will discuss in the TS diagram or in the vapor dome. Okay, that means whatever the substance which is coming out, it may be saturated vapor, that means complete vapor. Okay, complete vapor. Okay, and or it may be a mixture of vapor plus liquid. Okay, so whatever the thing it is, it will come to condenser. Okay, so in different cycles, for Carnot cycle, if you apply Carnot cycle, the substance for Carnot cycle, the phase with which the substance will come out will be liquid plus vapor. Okay, but if you apply Rankine cycle, then this is going to be saturated vapor. Okay, saturated vapor will read here. Okay, so now you remember that it would be, that means only vapor you can take. If you apply Rankine cycle, then this will come out with either with a saturated vapor, or the conditions will be given in the question itself. Okay, either it can be liquid plus vapor or it can be only vapor. Okay, so after that, whatever the thing is remaining, it will pass through the condenser. After passing through the condenser, what is going to be there? If it is liquid plus vapor, in the question it is maintained that the products coming out from the turbine is liquid plus vapor, then whatever the vapor part is remaining is going to convert it into liquid in the condenser. The condenser is going to condense the steam. Okay, and if it is mentioned that the products coming out of the turbine is completely vapor, then also whatever the vapor is coming out of the turbine is going to get converted into water in condenser. Okay, so in this way, so after condenser, whatever the water is coming out, that thing is again pumped by the pump. Okay, that means this is how the complete cycle works. Okay, in steam power plant. Okay, with the changes of phase in different places, this is how the steam turbine works. Now this TS diagram we have kept it empty because before understanding the TS diagram, okay, or the temperature entropy diagram for steam power plant, there is one particular thing which we need to understand, that is nothing but a vapor dome. Okay, this is known as a vapor dome. These vapor dome are lines. Okay, this is a dome which is made up of infinite number of points. Okay, now this thing will make us understand, okay, or this thing will make us represent the different phases of the substance, okay, in TS diagram. At what temperature, okay, at what temperature the substance is going to be liquid or vapor, the substance is going to be liquid or liquid plus vapor or completely liquid. Okay, so these things will be totally understood from this vapor dome. Okay, now if you consider this topmost point, the left side of the vapor dome, the left side of the vapor dome represents the saturated liquid. Saturated liquid means that is the point, or in this line, okay, at certain temperature or certain temperature, at certain temperature, this is the point where you can represent that there is only liquid, no vapor. Okay, there is only liquid, no vapor. Okay, this left side of that line is going to represent the saturated liquid. That means if you go slightly inside this dome, then your liquid will start to evaporate. Okay, your liquid will start to convert into steam. Okay, so this left line, okay, this left line is boundary for your, or if you can say this is a boundary or condition. This is a condition for you to understand that at this point, the liquid is going to have the phase of only liquid. If you slightly go inside this vapor dome, okay, if you cross this boundary, Okay, this boundary if you cross slightly, then your liquid is going to start evaporate. Okay, so the left side is what? The left side is nothing but only liquid. Okay, now at different points it is going to that means at different point of entropy it is going to show us the line. That means at this point, at this temperature, okay, the entropy at this entropy the liquid is going to be, the saturated liquid is going to be there. Saturated liquid is nothing but it is the at maximum entropy where it can be liquid. Okay, so at this particular temperature, this is the point or this is the entropy value where it can be liquid. Okay, maximum entropy value where it can be liquid. Now if you slightly increase the temperature, now what will happen? This is going to be your new entropy value. That means at this entropy and at this temperature, okay, your liquid can, or at this entropy your liquid can rise up to temperature this T2. Okay, this is T1 and this is T2, suppose. Okay, that means at this entropy value the temperature of your liquid can rise up to temperature T2. Then at this entropy it is going to have maximum liquid value. If you slightly increase the entropy value at the same temperature, then it is going inside the vapor dome, and inside the vapor dome completely represents the liquid plus vapor. Okay, liquid plus vapor. Now if you slightly increase the temperature again, then you are going to have a new, again another entropy value. Okay, now what does that mean? If you increase the entropy, now your water to be saturated. Saturated means what? Nothing, just at the verge of evaporating. Okay, it is just at the verge of evaporating. If you slightly increase the entropy, then it will turn into water again. Okay, so at this new entropy value or S3, if you can maximum go up to this temperature. Okay, if you go up to maximum this temperature, at this temperature you can have the saturated liquid. That means at the verge of evaporating. If you slightly increase the entropy, again it is going to be starting. Okay, the evaporation will start, and the remaining thing would be nothing but liquid plus vapor. Okay, so this is the importance of a vapor dome. Okay, and this line, okay, left line represents the saturated liquid line, and right part of the topmost point represents the saturated vapor line. Saturated vapor line means what? The substance has just finished the evaporation. Okay, just the small amount of liquid has just now has been converted into vapor, completely vapor. Okay, this line represents the saturated vapor line. Okay, that means what? In this vapor dome, the left part is going to be completely, okay, if any point is situated in the left side of that line, that means completely liquid. Okay, up to this boundary it can be completely liquid. Okay, up to this boundary it can be completely liquid. Now just inside the vapor dome, what it is going to be? It is going to be nothing but liquid plus vapor. Okay, now after that, if you increase the entropy, and if you reach up to this point is nothing but saturated vapor. Saturated vapor means what? Just finish the evaporation. So beyond this line it is going to be obviously vapor, and that vapor is going to be superheated vapor. Okay, this vapor is going to be superheated vapor. That means what? You can convert it into vapor up to this line only. Still you are increasing entropy, that means your vapor is getting superheated now. Okay, up to this line you are getting completely vapor. Now still you are increasing entropy, that means superheated vapor. Similarly, up to here it is going to be liquid. Inside this is going to be liquid plus vapor. Liquid plus vapor means what? Inside this is any point is there. Inside this any point or any line is there. That means in that line the entropy is increasing, but the substance is evaporating or changing its phase. Okay, the substance is changing its phase, and changing its phase means what? Inside this the temperature is always going to be constant. The phase changing temperature is always constant. You all know that. While you boil temperature, until and unless every bit of the water has been converted to vapor, okay, the total temperature of that vessel does not change. Okay, that means phase changing process is always constant temperature. Okay, so inside this the temperature is always constant. Okay, temperature constant line will be there. Okay, so to understand this we must know that this is our vapor dome. Okay, this is our vapor dome. Left side of the vapor dome represents always liquid, middle part always represents liquid plus vapor, and right side always represents only vapor. Okay, so now let us, we want to run this system on a Carnot cycle. Okay, let us, we now want to run this system on a Carnot cycle. Now if you represent the Carnot cycle, okay, if you represent the Carnot or Carnot steam power cycle, okay, we can say Carnot steam power cycle. Now let us suppose this is our vapor dome. Okay, now we all know that for Carnot cycle there is always a lower temperature, okay, and there is always a higher temperature. Okay, suppose this is TH and this is going to be your TL. This is lower temperature and this is higher temperature. So if you represent the steam power plant in Carnot cycle, okay, then this is going to give you your Carnot cycle in Rankine, okay, or a Carnot cycle in TS diagram. Okay, if you represent steam power plant in TS diagram, then this is going to be your Carnot cycle. And Carnot cycle in TS diagram is always square or rectangle, we all know. So this is going to be 1, this is going to be 2, this is going to be 3, and this is going to be 4. Okay, now what is going to be there? 1 to 2 is what? 1 to 2 is nothing but adiabatic compression. In pump, we know in pump always the things get compressed. Okay, so 1 to 2 is what? It is nothing but adiabatic compression. Since it is isentropic here, it is going to be adiabatic compression. 2 to 3 is what? 2 to 3 is nothing but heat addition. Okay, constant temperature heat addition. 3 to 4 is what? 3 to 4 is nothing but adiabatic expansion. Since turbine is there, there is going to be expansion. And 4 to 1 is what? 4 to 1 is condenser. Condenser means what? The thing is going to, or the remaining vapor is going to change into water vapor. Okay, now let us suppose this is 1. Okay, or this is 0.1. This is 0.1 means what? While coming from 4 to 1 at 0.1. Okay, if you remember, we have said that inside the vapor dome there is always going to be liquid plus vapor. Okay, that means what? In Carnot cycle, okay, the pump sucks in the liquid plus vapor. Okay, that means steam plus water it is going to pump. Okay, so after pumping, what is going to happen? It is going to reach 0.2. It is going to reach 0.2. That means what? Its temperature is increasing, but now it is getting into a saturated liquid part. Okay, previously it was liquid plus vapor, since it is 0.1. Okay, now after that in 0.1 to 2 it is going to be after pumping it is reaching a temperature of TH. Okay, now as we increase the temperature in vapor dome, according to the vapor dome, we have seen that if we increase the temperature, a slightly higher entropy is needed so that it can turn into vapor. Okay, so as we are increasing the temperature, keeping the entropy same, that is the reason it is reaching to a point where it is saturated liquid. Saturated liquid means what? It is on the verge of evaporation. Just now if you increase the entropy by a slight amount, this is going to evaporate. Okay, so this is going to reach a saturated liquid point. Okay, so after the heat addition, what is going to be happening here? After heat addition, that means what? The liquid part is now starting to evaporate. Okay, it is starting to evaporate. That means what? It will just evaporate up to 0.3. Till then it is going to be a constant temperature process. Why it is going to be constant temperature process? Because it is going to be phase change. Now since it is phase change, it will reach just 0.3. At 0.3 is what? 0.3 is nothing but it is your saturated vapor line. That means it will just finish evaporating. Okay, just finish evaporating. That means complete liquid has just been converted into steam. Okay, so it will come up to 0.3 as just steam. Okay, now after that it will expand in turbine. From 3 to 4 it is going to expand in turbine. After expanding in turbine, what is going to be there? After expanding in turbine, it is coming to 0.4. 0.4 is what? It is again inside the vapor dome. Okay, that means the product that is coming out of the turbine in Carnot steam power plant is going to be a mixture of liquid and vapor, and again it is again in condenser the temperature, some of the steam is going to get converted into liquid. Okay, and it will reach 0.1 again, and in this way this is going to the Carnot cycle is going to work. Okay, and the representation of Carnot steam power plant in the TS diagram is like this. Okay, now we will see how it is going to be difficult for us to run a Carnot steam power plant. Okay, now we are going to see the drawbacks of Carnot steam power plant. Okay, steam power plant is generally not Carnot. Okay, now since Carnot is a reversible or ideal cycle, okay, since it is an ideal cycle, so we are representing first in Carnot cycle. Now we are going to see what are the drawbacks for Carnot cycle, Carnot steam power plant. First of all, it is difficult to design a partial condenser. Partial condenser means what? It is very difficult to produce a condenser which will condense a limited amount of vapor into liquid. Okay, that means a limited amount of vapor will turn into liquid and the remaining will remain as same steam. Okay, now this is condenser. This 4 to 1, there in 0.4 was also a liquid plus vapor, or you can say it as wet region. Wet region means what? Instead of steam, there some amount of liquid is going to be there. Okay, now the end products of the condenser is again the liquid plus vapor only. Okay, end points of the condenser is again liquid plus vapor only. So it is difficult to design such type of condenser which will convert only a part of the steam into liquid. Okay, otherwise all the condenser condenses the whole amount of steam. So okay, so the first thing is difficult to design a partial condenser. You cannot design a partial condenser. That is an amount of or a part of the steam is going to get converted into liquid, the remaining will remain same, is not going to be possible. Second thing is very difficult to design a device to raise the pressure of a liquid plus vapor. From 1 to 2 we are raising the pressure. Okay, by pumping it, what are we doing? We are raising the pressure. Okay, now it is very difficult to design a device which is used to raise the pressure of liquid and vapor. Okay, that means the liquid, if there is a mixture of liquid and vapor, then to increase the pressure of this complete mixture is not going to be possible, or it is very difficult to design the device which is going to rise the pressure of liquid plus vapor. Okay, and the third thing is quality of steam at the exit is very poor. That means what? The inlet at this is the turbine work. Okay, 3 to 4 is nothing but a turbine work. Okay, that is a expansion, isentropic expansion is going on there. So the inlet at the turbine is what? Inlet at the turbine is saturated gas. Saturated gas means what? Just it has completed the evaporation process. Okay, so immediately we are putting it into the turbine, and in turbine due to the expansion, its temperature always comes down. Temperature and pressure always comes down. That means whenever the isentropic expansion is taking place in the turbine, the end products is in the wet region again. Okay, that means just after coming down, just at the inlet of the turbine, after that the whole path is in the wet region. Just the inlet of the turbine is at saturated vapor region. Okay, saturated vapor line. Okay, after that, just after that, every process, each and every point of the process is going to be in the wet region only. Wet region means what? Whatever the substance is coming out of the turbine is going to be a liquid plus vapor mixture. Okay, liquid plus vapor mixture. Now since the complete process is in wet region, okay, that means whatever the steam we are getting at the exit is of very poor quality. Okay, it is having a amount of, okay, that means it is having a significant amount of liquid also present at the exit. Okay, so the exit at the steam is very poor, and since it is liquid, okay, since liquid is traveling through the turbine instead of steam, liquid is passing through the turbine, the erosion takes place in the turbine very easily. Okay, so these are the drawbacks of a Carnot steam power plant. Okay, now we are going to analyze the Carnot steam power plant, and after that we will move to the Rankine cycle. As we all know, in TS diagram, constant pressure line always comes like this. Okay, now this is for air. This is for air. Okay, now in vapor dome, inside the vapor dome, the constant pressure line would be like this. Because in TS diagram, even if the pressure is constant, the temperature is going to be same inside the vapor dome. Okay, since the condense or the phase change is taking place, the temperature is going to be constant. Now in every other cases, if this is the TS diagram, with the if pressure is constant, heat addition or heat rejection used to take place. So for that, at constant pressure, we used to consider temperature is also going to increase by this amount. Okay, now in this phase changing process, inside the vapor dome, it is nothing but phase changing process. Phase changing process, temperature is always going to be constant. So inside the vapor dome, this is the constant pressure line also. Okay, now if it is just coming out of the vapor dome, then it will be as usual constant pressure line. But inside the vapor dome, the constant pressure line is going to be like this. Similarly, up to here it is going to be constant here. After coming out of the vapor dome, it is going to be same as that of constant pressure line as that of in case of air. Okay, so this is the difference here. Okay, now Carnot efficiency we all know. Okay, this thing we have derived several times. Okay, TH minus TL divided by TA. Now where is TH here? TH is nothing but higher temperature. Okay, higher temperature is what? This is going to be higher temperature. Okay, this is what? Saturated temperature at pH. Saturated temperature means what? Saturated temperature means at what temperature there is going to be just vapor. Okay, just the completion of vapor will take place. Okay, at certain pressure, at what temperature the liquid is going to just finish the evaporation process, that temperature. Okay, that means temperature at this point is going to give you the TH. Okay, and since the TH is constant for the whole process, you can take that the temperature is saturated temperature at pressure pH. Okay, now if you decrease the pressure, now your temperature would be here. That means what we know? We know that for a particular pressure, the saturated temperature is going to change. Okay, now from here, TH is, from this diagram, TH is what? Saturated temperature at pH. pH means what? Higher temperature, higher pressure. Okay, pH means higher pressure. Higher pressure is always constant. Okay, TH is always constant. Okay, now how can we find out? We can find out that at pressure pH. Okay, at pressure pH, what is going to be the saturated temperature? This is, at that point we are going to have the saturated temperature. This is nothing but TH. And TL is what? Saturated temperature at PL. That means at lower pressure, what is going to be the saturated temperature? This is going to be our TL. Okay, this is going to be our TL. Okay, now we can find out this. Now to understand the steam power plant, understanding the steam table is very much important. Okay, understanding the steam table is very much important. Now the certain pressure, it will be given in the question, certain pressure. Now in the steam table we need to find out at that pressure. Okay, at that pressure what is going to be the saturated temperature, that we can find out from the steam table. Okay, if you open a steam table, okay, if you open a steam table, you are going to find the saturated region. In that saturated region they are going to give pressures, random pressures they are going to give. Now suppose they have given a pressure of 1 bar. Okay, or 8 bar. Okay, suppose this is given as 8 bar, this is given as 1 bar. Okay, so these are the standard values of pressures. Okay, 8 bar is always given in the saturated region of the steam table. So from that you need to find out what is going to be the pressure at 8 bar. Okay, so we have found out the 8 bar pressure. Now alongside with it they will give what is the saturated temperature. Okay, the saturated temperature they will give. At 8 bar pressure, the saturated temperature they will give, that saturated temperature is going to be high pressure. Okay, or high temperature. Similarly, the lower pressure of 1 bar is also given. So you will find out from the saturated region of the steam table that where 1 bar is given with the 1 bar alongside this 1 bar. Okay, for this 1 bar, what is going to be the saturated temperature? That will be nothing but your lower temperature. Okay, so everything is supposed to be found out from steam table, but in gate you do not have the time to find out from the steam table. In gate they always provide the table. Okay, they always provide the table. In that table they always mention that at 8 bar pressure our saturated temperature is this, our enthalpy value is this, entropy value is this, internal energy value is this, specific volume is this, everything, whatever the part which is needed, they always provide it in the question. Okay, you need not find out the steam table for gate. Okay, but understanding this thing, you need to understand what is steam table. Okay, and finding the values from steam table. Now the first process we are going to consider here is nothing but 223 is isothermal heat addition process. Isothermal heat addition process is what? Now in that it is going from point 223. Okay, point 223, that means it is going into the boiler and coming out of the boiler. That means boiler is what? An open system. Boiler is what? An open system. Now if you find out what is going to be the first law equation for open system, it was nothing but H1 plus V1 square by 2G, something like that. Potential energy Z plus Q equals to H2 plus V1 square by 2 plus ZG plus W. Now if we neglect the potential and kinetic energy and potential energy changes, then this thing will get cancelled out. This thing will get cancelled out. Okay, and we can find out what is going to be the heat addition. Now in boiler there is not going to be any work, so W is always getting cancelled out. Now from here what is Q? Q is nothing but H2 minus H1. Okay, H2 minus H1. Now as it is going from H2 to 3, okay, H2 to 3, so it would be what? It would be nothing but H3 minus H2. From the first law you can find out what is going to be your Q in. Q in is nothing but H3 minus H2. Okay, so H2 is what? Now H2, how you can find it from a steam table? H2 is HF. HF means enthalpy of the fluid. Enthalpy of the fluid means what? At saturated line, okay, at saturated liquid line, what is going to be the enthalpy at that particular pressure? As we have said, in saturated region of the steam table, they will give a particular pressure. Okay, they will give a, and according to that they will give what is the saturation temperature at that saturation temperature at this pressure, enthalpy value at this pressure. That means saturated liquid enthalpy at that pressure, saturated gaseous enthalpy at that pressure. Okay, it will be always given in the question or in the steam table or in the question. Okay, now H2 is what? H2 is nothing but this point. At this point what is going to be the enthalpy? Okay, now you can find it from the steam table. Okay, so whatever the values of entropy or internal energy or enthalpy, everything which is having a point at this line comes with a suffix of small f, that is HF or UF or SF or BF, SF. Okay, this is entropy of fluid. Okay, that means at 8 bar what is going to be the enthalpy of the fluid? That means what is going to be the enthalpy of the liquid at this line is going to be given by HF. Okay, that means at this point, the points touching this line is going to have the enthalpy value of HF. Okay, now in the steam table they will give for the particular pressure HF value is given. Okay, that means at 8 bar the point lying here is going to have the enthalpy value of this, internal energy value of this, entropy value of this, specific volume of this. Similarly at the same pressure they will also give Hg. Okay, that means enthalpy for gas. Gas means whatever. Now at this point it is going to convert into vapor. At this point it is going to convert into vapor. Okay, so whatever the enthalpy is situated in this line is denoted by a suffix of G. Okay, now it is Hg, Sg, Ug or Vg. Okay, like that it is given. Okay, so H2 is what? H2 is nothing but fluid. Okay, enthalpy of the fluid at high pressure, and H3 is what? H3 is enthalpy of the gas at same pressure or high pressure. Okay, that means what? H2 is nothing but enthalpy of the fluid at high pressure. H3 is what? Enthalpy of the gas at high pressure. Okay, now if you take the difference of this is going to give you the amount of heat addition in that isothermal process. Now we are going for the process 3 to 4. 3 to 4 is what? Isentropic expansion. Okay, isentropic expansion. Now to understand this, there is a concept of dryness fraction. Okay, there is a concept of dryness fraction. So what does it mean? This is nothing but X. It is represented by X. Okay, and it is nothing but the ratio of the mass of the vapor and the mass of the vapor plus the mass of the liquid. Okay, this ratio is defined as dryness fraction. That is, X is known as our dryness fraction. Okay, now what does this mean? Okay, what does this mean actually? So this dryness fraction is what? Suppose you are taking a point at X at 4. Okay, at 4, what is the amount of vapor, that is what is the total amount of vapor present here? Okay, now as we have said earlier, inside the vapor dome it is a mixture of liquid and vapor. Okay, it is a mixture of liquid and vapor, and in this mixture there are two phases now, liquid and vapor. Okay, now the liquid part has certain amount of mass, the vapor part has certain amount of mass. Among this total mass, okay, total mass of liquid and vapor, what is the amount of vapor? Okay, what is the mass of vapor? Okay, that means in the total amount of the liquid and vapor, what is the fraction of vapor present in that mass? Okay, in that total mass, what is the fraction of vapor is going to be defined as our dryness fraction. Okay, now dryness fraction is going to have different values for different points in the TS diagram and in the vapor dome. The dryness fraction is going to be have a different value. Okay, is going to have a different value. Now, for example, as we have said that in the left line, okay, if you take this point, then in the left side of the point it is known as nothing but saturated liquid line. Okay, saturated liquid line means what? This is on the verge of evaporation. Okay, now whatever present in this line is completely going to be liquid. Okay, now if you want to take a point here and you want to find a dryness fraction here, what is going to be the value? Now we all know that in this line, whatever the point is there, this point is going to have a phase of complete liquid, nothing else. Okay, so complete liquid is there, that means vapor is going to be 0. Left side is complete liquid, middle one is liquid plus vapor, right side is completely vapor. So in the line there is completely liquid. Okay, nothing vapor, no vapor is there. So mass of vapor is going to be 0. Okay, mass of, suppose this point is 1 dash and this point is suppose 4 dash. Okay, so if you want to find x1 dash, okay, dryness fraction at a point x1 dash, what it is going to be? The mass of vapor is going to be 0. Mass of vapor is going to be 0. So the dryness fraction at this point is going to be 0. Okay, now if you want to find the dryness fraction at the point 4 dash, okay, so what it is going to be? X or dryness fraction at the point 4 dash, what it is going to be? Now as we have said, this is saturated vapor line. Saturated vapor line means what? The liquid has just converted into or just completed its evaporation. Okay, now whatever the substance is present in this line is going to be in complete vapor phase. Okay, so no liquid is there. As there is no liquid, that means what? Now at point 4, this L is going to have 0 value. Okay, this M is going to have 0 value. Mass of vapor we do not know, but we know that if this is value, this is 0, then this one and this one will cancel out and give us a result of 1. Okay, so this is going to be a result of 1. That means the value of dryness fraction at any point in this line is going to have a value of 0. The dryness fraction at this line, okay, in this line is going to have a value of 1. Okay, so in between whatever the dryness fraction you need to find is going to be always in between 0 and 1. Okay, now the dryness fraction is what? Dryness fraction helps us to find out what is the quality of steam. Okay, the quality of steam is good or bad, that is defined by our dryness fraction. If the dryness fraction is having a value of 0.94, that means what? 94% of the 94% is vapor among the total amount of, that is mass of liquid plus mass of vapor. Among this total mass, 94% is going to be vapor. 94% is going to be vapor. Okay, now if you are saying that dryness fraction is nothing but 0.18, then the quality of steam is going to be very less. Okay, only 18% of it is going to be vapor. Okay, so this is going to be our dryness fraction. Now let us come to the analysis. Okay, for analysis we have chosen the process 3 to 4, that is isentropic expansion. Okay, now in isentropic expansion it is 3 to 4. 3 to 4. Okay, so 3 is what? 3 is nothing. At 3 point is what? 3 at point 3, this is going to be, but that means the substance is going to be in completely vapor state. That means the substance should be just finished its evaporation. Okay, at this point it is going to be complete vapor. Okay, now S3. Okay, this is entropy process. This is 3 to 4 is nothing but isentropic process. Okay, that means at point 3 and point 4 the entropy is going to be same. Okay, now how can you find entropy at point 3? How can you find entropy at point 3? With the help of steam table. Okay, now this pressure will be given. Okay, pressure value will be given. Okay, suppose it is having a pressure of 8 bar. It is having a pressure of 8 bar. Okay, now in steam table you are going to go to the saturated zone. Okay, you are going to the saturated zone, and in that saturated zone there will be a pressure called 8 bar. Okay, now in that 8 bar, okay, in that pressure, in that line of 8 bar, there would be certain values. Okay, there would be certain values. In that you will find values like HF, HG, SF, SG. Okay, like we have told earlier. Okay, so in that thing at pressure 8 bar, okay, at pressure 8 bar, okay, it is going to have certain value. Okay, at pressure 8 bar, HF, HG, SF, HG, similarly internal energy UG, UF, certainly certain things are going to be there. Now you are going to get the value of P saturated. At the 8 bar you are going to have HF. Okay, you are again going to have some value of HG, you are going to have some value of SF, you are going to have some value of SG. Okay, now at 8 bar the SG value, at 8 bar the SG value, G means what? Gaseous state. Okay, the at 8 bar the entropy at the gaseous state, that means the entropy at this point is going to be given. And SF is what? SF is nothing but entropy at this point. F means fluid here. Okay, in the fluid line what is going to be the entropy at 8 bar is going to give the entropy at this point. Okay, at SG at 8 bar is going to be, this is the gaseous, that means in gaseous line at 8 bar this point is going to have the value of this much entropy. Okay, so this thing will be given in your steam table. Okay, if not in steam table, in question they will shortly give us a small table. In this the sufficient amount of information will be given. Okay, now from there what you can find? Okay, what you can find? Now you are not given the mass of liquid. In this point you are not given the mass of liquid. You are not given the mass of liquid, mass of vapor, anything is not given. Still you need to find what is going to be the dryness fraction. Okay, because the dryness fraction is a certain thing which holds the relation. Okay, which holds the relation to find out the enthalpy or entropy or internal energy or specific volume inside the vapor dome. Okay, the only relation that can help us is going to be our dryness fraction. Okay, so at a certain point if you find that value of a dryness fraction, you can easily find the corresponding values from steam table. Okay, and you can find entropy value, enthalpy value, everything from this point only. Okay, now how it is going to be, we are going to show. Okay, now as we know 3 to 4 is nothing but isentropic process. 3 to 4 is nothing but isentropic process. Okay, 3 to 4 is, so S3 is going to be equal to S4. Okay, S3 is going to be equal to S4. Now at any point inside the vapor tube, okay, either it may be entropy or enthalpy or anything it may be. Okay, it may be U4 or it may be V4. Okay, that means at points inside the vapor dome at a certain point the relation is given like this. If it is given the entropy, you need to find entropy at point 4. This is nothing but SF plus X at 4 into S of Fg. SFG is what? SFG is nothing but Sg minus Sf. This is written in terms of, this total thing is written in terms of SFG. Okay. Now all the relation is going to be same. This is also going to be same. HF plus X at 4 into HF minus, sorry, Hg minus HF. Similarly, everything is going to be same. Each and every point is going to be same. Now, how can you find out what is going to be the enthalpy here? Now we have found out that S3 is equal to S4. Okay. Now going to steam table at point 4, at 8 bar. Okay, at 8 bar, the value of Sg is going to give our S3. Okay, so you already know S3. Now you also know that 3 to 4 is an isentropic process. So entropy at point 3 and entropy at point 4 is going to be same. So you have equated it to S4. Okay, you have equated it to S4. Now in this equation you already know S4. You already know S4. From the steam table you are going to find SF. Okay, that means it is going to have a pressure again. Suppose this is going to be pressure equal to 1 bar. Okay, now if you take in steam table, if you go to the pressure of 1 bar, you are again going to have some value of SF and some value of Sg. Okay, now as you are finding at a particular, this thing is going to be for a particular pressure. Okay, so S4 is at what pressure? S4 is at nothing but at pressure equals to 1 bar. So you will go to steam table. Okay, you will go to steam table. Okay, at 1 bar you will find a value of SF. SF means what? At fluid line, what is going to be the entropy? We will find at 1 bar. Okay, so this value you will put here. Okay, and here, because SF we are going to use twice. Okay, similarly at 1 bar, what is going to be Sg? Sg value will also be given. Sg value will be at gaseous line. What is going to be your entropy at 1 bar? Okay, so this thing you will put here. Now you know this one, this one, this one, and this one. Only thing unknown is X4. You can easily find what is going to be your dryness fraction. Okay, now you have completed finding your dryness fraction. Okay, now you have completed finding your dryness fraction. That is X4 you know now. Okay, similarly you want to find enthalpy at point 4. Enthalpy at point 4. Okay, now HF would be found out from here again. At pressure 1 bar at fluid line, what is going to be the enthalpy? You can find, you can put it here. At pressure 1 bar from the steam table, you can find what is going to be your Hg. Okay, you can find what is going to be your Hg. So Hg means what? Enthalpy at gaseous line at pressure 1 bar. You can easily find and put it here. Okay, you can easily find and put it here. Now X4 you have already found out from the previous equation. You put X4 here. Okay, you can find out what is going to be your enthalpy at point 4. Okay, this thing I am saying because if you want to find out what is going to be the work done by turbine, 3 to 4 is going to be your work done by turbine. And from the first law we have seen that work done by turbine is nothing but the enthalpy difference. Here it is going to be S3 minus H3 minus H4. H3, how can you find H3 now? That means enthalpy at this point. How can you find this? At pressure 8 bar. This is at pressure 8 bar. At 8 bar of saturated pressure. Okay, what is this? Is going to be your gaseous line. Okay, at gaseous line, what is going to be your enthalpy value? At gaseous line, what is going to be your enthalpy value? So this value will be our H3. This value will be our H3. And what is H4? H4 is this one. You have just found out H4 from this equation. Solving these equations, you have found out H4. Okay, so to find out the work done by turbine, we need enthalpy difference. And to find enthalpy at a point inside the vapor dome, to find enthalpy at a point inside the vapor dome, you need dryness fraction. Okay, you need dryness fraction. And how to find dryness fraction? I have just told you how to find dryness fraction. equating the entropies, okay, equating the entropies and finding the value of entropy at fluid line, entropy at gaseous line at different pressure. You are going to find the dryness fraction, and after you find the dryness fraction, you can put it in these equations. Okay, now these are the equations which are going to be very important. These should be in your mind all the time while solving the questions. These things must be in your mind all the time, you cannot forget. Okay, so 3 to 4 isentropic process. From that, what it is done, 3 to 4 is nothing but our work producing process. Okay, for work producing process, how to find out the work done by turbine? We need to find out the enthalpy difference, and this should be found out considering these processes. Okay, so after that 3 to 4 we are going to analyze for another process. Till now 3 to 4, after the analysis we have found out what is going to be the work done by turbine. Now we are going for process isentropic compression process. Okay, so 1 to 2 is nothing but isentropic compression process. 3 to 4 was our isentropic expansion process. Now you may say, after 3 to 4 why have we gone without going for 4 to 1, we are going to 1 to 4, because from the process 3 to 4, okay, equating with the properties at point 3, okay, equating with the property, that means entropy at point 3 was equal to the entropy at point 4. Considering that, we have found out all the relations and all the things, enthalpy, internal energy, all the things we have found out considering this point. Now 1 and 4 is not going to have any common point or anything that is equal, except for the pressure and temperature. There is nothing same that we can say. Okay, that means entropy, enthalpy at point 4 and point 1 is nothing same. Only the temperature at point 4 and 1 is same, and the pressure is same. Okay, entropy, enthalpy is not same. But if we want to find out the W net, if you want to find out W net, net means what? Work done by turbine minus work done by pump. Okay, to find out this, we need to find out work done by pump, and work done by pump is again nothing but H2 minus H1. Difference between the enthalpies. And to find out the enthalpies, we need to find what is going to be the enthalpy at point 1. And to find out the enthalpy at point 1, we need to find what is going to be the dryness fraction at point 1. Okay, to find the dryness fraction at point 1, we need to equate with a standard value. Okay, so in this 1 to 2, in this process 1 to 2, entropy at 1 and entropy at 2 is going to be same. Entropy at 1 and entropy at 2, since this is isentropic compression process, 1 and 2 entropy value is going to be same. Okay, now S2 is what? S2 is nothing but entropy at fluid line at high pressure. Okay, so this is going to be your high pressure line, and this is going to be your low pressure line. This is going to be low pressure line. Okay, so at high pressure line, from the steam table at the high pressure line, okay, or at high pressure, that means high pressure is going to have a constant value, suppose 800 bar. Okay, so at this 800 bar, what is going to be the entropy at the fluid line is going to be the entropy at point 2. Entropy at point 2. Okay, so here we can find out easily S2. Now we know that S2 is again same to S1. S2 is again same to S1. Okay, so again there is an equation. Sorry, this is going to be 1. There is an equation. S1 is what? S1 is nothing but SF. SF means what? SF means at this point, not at this point. Okay, it is also SF, it is also SF. You can rather write SF at point 2, okay, or SF at pH. SF at pH, okay, or here you can write SF at PL. PL means at lower pressure. At lower pressure, suppose this is 1 bar. Okay, suppose this is 1 bar. At 1 bar, okay, you take 8 bar. Okay, it is not possible to compress from 1 bar to 800 bar. So 8 bar and 1 bar. At 1 bar, okay, at 1 bar, what is going to be the SF value? That means that at 1 bar at fluid line, what is going to be the entropy value? Is this. Okay, plus X1. X1 is nothing but at this point what is going to be the dryness fraction. That means what percent of vapor is present among the combination of liquid and vapor, what percent of vapor is present. Okay, X1 into SFG. SFG means what? SFG is nothing but the difference of Sg and Sf. Sfg is what? Sfg is nothing but Sg minus Sf. Sg is what? Sg is nothing but at lower pressure. Okay, for this case, for S1 at lower pressure, at gaseous line, what is going to be the entropy? Okay, at gaseous line, this you can directly find out from the steam table. Okay, you can go to the saturated zone, and in that you will find the pressure 1. You will find the pressure 1 bar. Then after that you are going to find Sg and Sf at this pressure. Then you can find S1 again. Okay, so S1, so you can find Sf, Sfg you can find. Okay, that is Sg minus Sf you can find. S1 you have already found out, because S1 is equal to S2. You can already find this. So from this equation, this is known, this is known, this is also known. You need to find x1. Okay, as you have found out x1 now you can easily find out h1. H1 is what? H1 is nothing but again hf plus x1 into h of hfg. Okay, so from this point you can easily find h1. Okay, so this is nothing but work done by pump. Work done by pump is what? H2 minus h1. H2 minus h1. And how can you find H2? Again similar way, H2 is nothing but at higher pressure. That means at 8 bar pressure, what is going to be the value of HF? At fluid line, what is going to be the value of enthalpy? Is going to give you your H2, and H1 you will find out from here. So you can find out work done by pump. Okay, so that is the reason we have taken after 3 to 4 we have taken the process 1 to 2. Okay, now we are going to consider 4 to 1, because all the values at 0.4 we can find out. Okay, now, and all the values at 0.1 we can find out if we find out the dryness fraction. Okay, and we have a steam table, then we can find out all the values as 0.1, and in the previous board we have found out all the values at 0.4. Now we are going to find out the heat rejection process. Our next process is heat rejection process. Okay, heat rejection process, that means 4 to 1. Okay, 4 to 1 is nothing but a condenser. Condenser is nothing but 4 to 1. Okay, if you remember the diagram, 4 to 1, the heat rejection process, there was a condenser. It used to convert the gaseous things which was coming out from the turbine. It used to convert them into liquid again. Okay, so this was the condenser. Condenser was an open system. So if you remember what was the first law for open system, it was nothing but enthalpy. Now it is coming from 4 to 1. Okay, so our initial condition is 4. Okay, initial condition is at 4. It is coming up to 0.1, so our final condition is at 1. Okay, so we have written H4 plus V4 square plus that, all the terms we have written, which we have written for the first law for a open system. Okay, now if you neglect the kinetic energy and potential energy changes, this is going to be like this. Okay, now another thing is there, in condenser we used to reject the heat. Reject the heat means heat was coming out of the system. Heat was coming out of the system means it was always negative. Okay, so in place of plus it is going to be negative. Okay, so from here what you can write, Q is minus, Q is nothing but H1 minus H4. Okay, so from here Q out is nothing but H4 minus H1. Okay, so if you want to find out what is going to be the heat rejection, it is again nothing but the enthalpy difference between the 2 points H4 and H1. That enthalpy difference will give you what amount of heat has been rejected. Okay, so now after considering all the processes, we have found out all the things. Now the remaining thing is our nothing but efficiency. Efficiency is what? Efficiency is nothing but what is the net work output you are going to get divided by what is the energy input you are giving. Energy input you are giving is nothing but Q in. Okay, so W net is what? Work done by turbine. What was work done by a turbine we had found out. Work done by pump we have also found out, divided by Q in. What was the amount of Q in? That was also found out. Okay, so if you put all these values here, you can easily find out what is going to be our efficiency for Carnot steam power plant. Carnot steam power plant. Now this thing is generally not used in practical cases. Okay, in practical cases Carnot steam power plant is not used. The thing or the cycle which we generally use in power plant cycle, we are considering this because this is Carnot cycle is an ideal gas. Okay, it is the ideal cycle for every other cycle. Okay, and this Carnot cycle is going to have the highest efficiency if the temperature difference is given, the Carnot cycle is going to have the highest efficiency. Okay, so if you take any process, either refrigeration, either steam power plant, either air standard, everything, for every cycles, Carnot cycle is the ideal cycle. Okay, for all the cycles it is the ideal one. Okay, so we are considering the ideal cycle, but it is not practically used. The practical cycle which is used for steam power plant is nothing but Rankine cycle. Okay, the Rankine cycle is found out. Now in the next lecture we are going to see the analysis of Rankine cycle and what processes constitute the Rankine cycle and how it is represented inside and outside the vapor dome at temperature entropy diagram. All this we are going to find out in the next lecture. Okay, so our next lecture is going to be on Rankine cycle. So Carnot cycle is up to here. Okay.